Hopefully you're familiar with the Chernobyl nuclear accident. Where is Chernobyl? Thank you. At least you didn't say Kansas. Suppose 10 grams of plutonium was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? The half-life of plutonium-239 is 24,100 years. So, are we going to use the half-life formula? No. The half-life formula is terrible compared to what we are doing in this section. That would be the broken wooden sword method. We don't want the broken wooden sword method. So, what do we do? Preferably, yeah, let's use this equation right here. And then what do we do? It's exactly what we did yesterday. Yeah. So, what are we given, basically? We're given 10 grams of plutonium, which is awesome, by the way. When? When t is 0. So we have an ordered pair of 0, 10. We need another ordered pair because we have two unknown things here. Oh, you're close. Yes, there you go. The half-life is 24,100, and after one half-life, how much will be remaining? Half, so 5. So the ordered pair is 24,100, 5. That is everything we need to be able to write the actual equation for this problem and then come up with the answer. So what do we do first? Plug in what? Good, that's the easier looking one. So what do I write? Okay, K0 is, K times 0 is 0, so e to the 0 is, so C times 1 is 10 equals C. Fairly easy to come up with there. Before I go on, what do you notice about C? No.
Oh, it's the grams we started.
It seems to be the initial amount. Yeah. When time is 0, it's going to wipe out the exponent and the e, and I'm just left with the c. So it seems like this number right here, this c, is going to be your initial amount. All right, so now we have y equals 10e to the kt. What do we do? We need to find k, so we plug in our other ordered pair. What do I write? Okay. Now what? No. Divide by 10 to both sides. And 5 divided by 10 is 1/2 equals e to the k times 24,100. And what do you notice about this number? It's a half. Coincidence? It's a half-life problem. Yeah. All right, so now what do we do? Continue solving for k. Natural log of both sides to wipe out the e. And what do I wind up with? Equals k. All right, now we have to write the equation, and we're going to need a decimal version of that because there's no way we're going to write that in our exponent. But you want to keep track of the fact that we have this sitting here for k. That'll come into play later on. So what do we get for k? 0.0000. I need more than that. That's all it gives you?
Yep.
28761. There. You do not want to have just two significant digits in your answer on these problems. If you round to the nearest, or to the first digit, or to the second digit that they give you, you're going to wind up with a wildly inaccurate answer. And then on the AP exam, it will be definitely wrong. So you want to be as accurate as you possibly can here. With all these zeros, these don't count. We actually only have 5 digits here. When you go to enter in some sort of calculation, you might use this instead of this, because this is exact and unrounded, whereas this one is rounded no matter what you do. All right, so regardless, our equation is y equals 10e to the negative 0.000029761 t. We're not done, but that's the equation. I'm putting a box around it so that it pops out of the page at me. A lot of times these problems will ask you to write the equation, which you have to do anyway, and then find the answer. So how long will it take 10 grams to decay to 1 gram? What do we do? Put in 1 for y, because y is the grams. T is time. We're looking for how long, so we've got to solve for t. 1 equals 10e to the negative 0.000029761 t. Now what? Divide both sides by 10. So I'll make this 1/10, and I'm just going to get rid of that 10 sitting there so I don't have to rewrite it. Natural log of both sides. And divide by k. So we have the natural log of 1/10 over negative 0.000029761 equals t, which is what? $80,058.5, so let's call it 80,059 years. 10 grams of plutonium, not very much at all. And it's going to take that long, and we still have 1 gram remaining. All right, so just to show you the difference, if I call that just negative 0.000029, and then I go ahead and do that division right here. So I'm going to take the natural log of 1/10, and then get outside the parentheses, divide by that rounded answer, negative 0.000029. Look at how different that answer is. I mean, it's in the same ballpark, 80,059 compared to 79,399.5. They're close to each other, but they're vastly different. And it's just because of that rounded answer that we entered in, that 0.00029, rather than using the actual answer that we got here. The exact answer here would be to use, instead of even this, when you enter in that k. Or go back up to the answer that you got when you found k. So let me re-enter this. The natural log of 1/10. And then divide by, and then go back up to that answer. Select the answer, bring it down, and then press enter. And now you have an exact result. Even though it was showed up here when you selected up here, it showed a decimal approximation, the calculator will still know that you mean to use what you entered in. So you can use that. Or you could go up and, instead of going to the decimal, go to the actual entry that you made and press enter to bring it down. That way you keep an exact answer, and this is what AP is going to be looking for. You cannot round until the very, very end. All right, our next problem, a population of fruit flies increases exponentially, and let me tell you, it does. There were 100 flies after the second day and 300 flies after the fourth day. Not quite accurate. There was actually more than that. More, way more, but that was my fault. How many flies were in the original population? and it says use days for time. So keep that in mind. We have a population of fruit flies increasing exponentially. As soon as I see that, I know I'm using this formula here. There were 100 flies after the second day and 300 flies after the fourth day. What do we do?
Well, let's get some ordered pairs.
Yeah. Ordered pairs is a good start. So what do we have? Good. Time is my independent variable, 2 comma 100. And what's my other ordered pair? 4 comma 300. All right, so let's plug something in. What do you want me to write? 100 equals. Somebody tell me 2? Terrible. Terrible. All right. I can't fire him, though, because I fired everybody else already.
No, I'm not fired.
I kind of just quit.
I believe it should be C e to the k times 2. Does that do anything for us? Not really. Okay, so let's set up the other ordered pair. What would that one be? 300 equals C e to the k times 4. Does that do anything for us?
Okay, wait.
Waiting.
I don't want to say it.
Solve for C.
Yeah.
Solve for C.
Divided by C, because then it would still be on.
But then what? Solve for C and then what?
And then set the equations out, like we have two equations here.
All right, I like what you're thinking, though. What we have here is a problem because we have two variables, basically, right? They're constants, but in this situation, we treat them like variables because we don't know what they are. We have two variables, which means to solve, we need two equations. And we currently have two equations. So just like in Algebra 1, when you had two equations and two variables, you had a bunch of methods you could use to solve. One of them was substitution. And this is where you have to trick. If you remember last time I was talking about you have to trick sometimes these problems into letting you find those two values. So we are going to solve one of these equations for C. Which one do you want to use? The top one. Halfway right. Let's use the top one. What do we get? No. Yeah. C equals
100 divided by
e to the 2k. That's right. Now I'm going to rewrite that, and you'll see why I'm going to rewrite that in a second here. But I'm going to rewrite this as what?
100 times.
Yeah. 100 times e to the negative 2k. That's going to make my substitution a little bit simpler. So now that I know what c is, 100 e to the negative 2k, I can substitute that in right there, which gives me 300 equals 100 e to the negative 2k times e to the 4k. Now, what can I do to simplify that? Right, those are like bases, and when we have like bases being multiplied, we add the exponents. So we wind up with 300 equals 100 e to the 2k. And now we have just one variable, and it's easy to solve. So what do we do? Divide by 100, so now I have 3 equals e to the 2k. Natural log of both sides. And I have, can I go straight to k equals? K equals natural log 3 divided by 2, which is what? .5493. Again, that's a rounded answer, so if you're calculating something, you don't want to use that, but that's going to be good for us to write an equation down. What is my equation? Do we know C?
Well, okay, wait, but we found K, and we can plug K into C and then have it do with that.
What good is a C without a K? The equation as it stands right now is CE to the 0.5493T. We don't know C right now. But you're right, we could take this K value that we found right here and plug it into this equation to find C. Or you could plug it into this equation with your other ordered pair to find C. I'd rather go up here. So let's find C. C equals 100 divided by e to the 2 times 0.5493. Now remember, we're not going to use the rounded value there. What do we get? 33.3 repeating. So now I do have a final equation, y equals, can you have 0.3 fruit flies?
No.
So let's call it 33 e to the 0.5493 t. Now what? Solve for t. Solve for t. Is that right?
We just have to know when T is 0.
Right. It says how many did we have in the beginning? In the beginning, the time was 0. So if I plug in 0 right here, I get 0 here, which makes e to the 0, which is just 1. So I wind up with 33 fruit flies. You needed to find C, which means you needed K. So there's your answer. There are 33 fruit flies in the beginning. So Wall Drug stops advertising. 4 months after they stop advertising, the owner notices that the sales have dropped from $100,000 a month to $80,000 a month. If the sales are decaying exponentially, what will they be after another 2 months? What do we do first? Find your ordered pairs. My ordered pairs are what? 0, 100,000.
That's what I meant. I didn't write
And 4, and we're using units of months here, 80,000. Okay, now what? Because it's 4 months later.
4 months after they stop advertising. The first 2 words.
4 months after Wall Drug stops advertising. Okay, so the first ordered pair, we plug it in, and what do we get?
C equals 100.
C equals 100,000, yeah. So we have y equals 100,000 e to the kt. Now we can plug in our other ordered pair. So I have what? 80,000. Okay? Hopefully you've noticed that there's kind of like a standard procedure to follow in these types of problems. So now we divide both sides by 100,000 and we wind up with 4/5 equals 4k, sorry, e to the 4k. Natural log of both sides, and then we divide both sides by 4. So we have the natural log of 4/5 divided by 4 equals k. So what do we get for k?
Negative 0.0552766.
We're going to use the actual answer that we got, not the rounded answer. And does the negative sign here make sense? Yes, good. Now what? So our equation is y equals e to the negative 0.0558 t. And what are we looking for here? After another 2 months. Another 2 months is the key. What do we have to plug in? Yes, because 6 months since the beginning is what we have to find. So we plug in 6 for t. Y equals 100,000 e to the negative 0.0558, and use the actual k that you came up with times 6. What do we get? $71,500. Newton's law of cooling, one of the most important things of the entire year right here. Very important law, simply states that a body or object will cool at a rate that is proportional to the difference between the body and the ambient temperature. The ambient temperature is the fancy way of saying the surrounding temperature, or the temperature of the room. Okay, so the ambient temperature in this room is probably about 71 degrees. The ambient temperature outside is whatever the temperature is outside. Put simply, in the language of calculus, that is Newton's law of cooling. It says the rate of change of the cooling body is proportional to the difference between the body temperature and the ambient temperature. Okay, so T sub B is body temperature, T sub A is ambient temperature. So think of y prime as the rate of change of the body's temperature over time. As this body is cooling, it is cooling at a rate. So let's suppose a dead body is lying in a room, held at a constant 60 degrees Fahrenheit. So I don't know what room that would be. Probably like my living room. Okay, so one of those rooms. A room that's actually cool. So this dead body was 100 degrees, and now it's 90 degrees 10 minutes later. How much longer will it take for this body's temperature to decrease to 80 degrees Fahrenheit? And do you understand that it will continue to decrease because the ambient temperature of the room is 60 degrees, which means that the body will tend towards that temperature. Okay? It'll try to find equilibrium with the room. So it's going to decrease, continue to decrease from 90 degrees. We want to know how much longer it's going to be until this thing is 80 degrees Fahrenheit. And we're going to do that using Newton's law of cooling. It is a law. It has to follow this law. So to do this, set up the equation, this guy, as dy over dt equals k times y minus 60. Why is it y minus 60? That is the ambient temperature, the temperature of the room. That's right. That's a constant. It says in the problem that it's held at a constant 60 degrees, so we can plug 60 in there. What is that y doing there then? Of what? That's the body's temperature. That temperature is changing, so that's going to be my variable. And since I'm using dy over dt over here, I'm going to call this y. The rate of change of the body's temperature over time is proportional to the body's temperature minus the ambient temperature. All right, so that's why that's a y sitting there. So we're going to do a separation of variables, integrate, and then substitute in our initial values to find out our c and k. So I need to change pages. And then apparently I need to zoom in. Maybe not that much, though. That's terrible. All right, I'm stuck with that. So we have dy over dt equals k times y minus 60. We need to do a separation of variables. What do we need to do here? Separation of variables means get all the variables on one side for one and get all the other ones on the other side. So the dt needs to go over here. This y minus 60 needs to go over here. So I wind up with 1 over y minus 60 dy equals k dt. Yeah, we got to integrate because we got to wind up with an equation that kind of looks like that. What is the integral of 1 over y minus 60 dy? The natural log of the absolute value of y minus 60 equals. K is a constant. Kt plus C. And I'm going to call that C1. You'll see why. A constant's a constant. I'm going to call this one C1 so we can see how things change as we go, if they change. All right, now what? No. We were trying to solve for y. What do we got to do? Trying to solve for y. No. Solve for y. Yeah, we're going to apply e, make a base of e to both sides. But before we do that, let's think about this absolute value thing here, because absolute value is a bummer to have to deal with. Do I need the absolute value? Yes, that is the logic you need. The body's temperature is more than 60 right now. So no matter what, it's going to be above 60 degrees, which means we will never wind up with a negative result here. So I do not need the absolute value symbols. I can apply the base e to both sides, and I'm left with just y minus 60 equals e to the kt plus c1, which is actually good. E to the kt times e to the c1, which is actually c e to the kt. I could call that c2 because now we have a different constant, but I'm going to call it c. We move this negative 60 over. Y equals c e to the kt plus 60. It's basically the same equation with one big difference. The ambient temperature is added on. Okay, so now what do we do? Find ordered pairs, good. We have 0, 100. When time is 0, the body's temperature is 100. 10 minutes later, the body's temperature is 90 degrees. And by the way, that's from when we measure it, not from when the body died. We weren't standing there watching it die. It was dead. And we measured its temperature, and that's when time started. So now what do we do? If I plug in the 0, 100, I have, this is 0 here, so that's c plus 60 equals 100, which means c equals 40. So I get c equals 40. So now my equation is y equals 40 e to the kt plus 60. Now from here, our goal is going to be to find k. Other ordered pair, we have 90 equals 40 e to the k times 10 plus 60. Subtract 60 from both sides and divide by 40, and we wind up with 3/4 equals e to the 10k.